Hello and welcome to lecture 27. So, in last lecture we were discussing about say numerical, where we have solved a numerical for the flying condition at 33,000 feet for Mach number 0.9, where we have temperature and pressure as 222 Kelvin and 26.2 kilopascal. We have done our calculation for say exit parameters, cycle parameters from intake, fan, compressor, combustion chamber, turbine, tailpipe, say turbine nozzle as well as fan nozzle, and we have done the final calculation for the velocity at the exit from both the nozzle, and we have done the calculation for the area. Now, our next target it is to calculate the performance parameters. So, let us start with this performance parameters. So, very first performance parameter we have is our total thrust or net thrust. That is what we are representing by cold thrust and hot thrust. For this cold thrust we can write down m dot f V10 minus V infinity plus A10 P10 minus P infinity. Same way for the hot side we can write down m dot core into 1 plus f V9 minus V infinity plus area into P9 minus P infinity. So, here in this case we have all these numbers available with us. Say fan flow rate we know it is 30 kg per second, for core mass flow rate it is 15 kg per second. Exit velocity we have calculated from the fan nozzle it is 327.7. Same way exit velocity from the core engine is 566.6, and we have our calculation for the pressure, and we have found both the nozzles are choke nozzle, and for that if we will be putting this number, the net thrust is coming 13.46 kilonewton. So, if you compare this number we will be doing very soon, this net thrust under ground condition we were getting it was around 20 kilonewton, and for the flying condition this thrust is coming 13.46 kilonewton. Now, let us do the calculation for the thrust specific fuel consumption. This thrust specific fuel consumption we are writing as 0.0252 into 15 divided by the thrust what we have calculated, and this is giving the thrust specific fuel consumption as 0.028 gram per Newton second. Okay. Now, we will be doing the calculation for our efficiency parameters. So, very first efficiency we have is propulsive efficiency. In last numerical when we were solving it was ground condition, for which my Mach number was 0, my velocity free stream velocity was 0. Here in this case we have our velocity known to us based on Mach number 0.9. So, V infinity is 268.8 meter per second. So, let us put this number. We have done calculation for total thrust. We have velocity values V9 and V10. Putting these numbers it says propulsive efficiency is coming to be 83.14. Now, you can imagine this number, it is a big number in itself. If you compare this with your turbojet engine, this number it's somewhat different. Same way, let us try to do the calculation for the thermal efficiency. This thermal efficiency we are writing the denominator part. So, there is a way of remembering this equation. Denominator part we will be putting here on numerator, and you are having the heat input it is mf into qr. So, if we are putting this number, the thermal efficiency is coming to be 26.78. Okay. And we have our overall efficiency, it is thermopropulsive efficiency, it is nothing but propulsive efficiency into thermal efficiency. We have this number, this efficiency is coming to be 22.27%. Okay. So, let us put this in terms of our conclusion table, where it says like we are having our temperature, pressure, area at the exit of my core nozzle, area of my fan nozzle, total thrust, we have thrust specific fuel consumption and all three efficiencies. Now, as we are doing for almost earlier cycles, let us try to discuss the effect of different cycle parameters on the performance parameter for this engine. So, it says like we will be discussing our results in terms of thrust or specific thrust, thrust specific fuel consumption. We have fuel air ratio, propulsive efficiency, thermal efficiency, overall efficiency. That is what we are correlating here in terms of fan pressure ratio, LP compressor pressure ratio, HP compressor pressure ratio. Since this is single spool configuration, so we will not be having this LP compressor and HP compressor. We are considering as a single compressor. So, we will take that as a compressor pressure ratio. We have bypass ratio for this turbofan engine, turbine entry temperature, different efficiencies, and here in this case we are discussing our results under the flight condition. Okay. So, let us try to discuss these results. Very first we will be taking the effect of fan pressure ratio. We are putting compressor pressure ratio, turbine entry temperature, bypass ratio and mass flow rate to be constant. So, let us see what is happening here. So, here in this case we can say by increasing the fan pressure ratio, my cold thrust, that is what is going to increase. At the same time the hot thrust is decreasing. So, somewhere here this is representing the design condition and summation of these two, that is representing my total thrust. Okay. Now, again we need to remember, since I want to increase my fan pressure ratio. So, it is obvious in order to achieve that pressure ratio, we need to have higher amount of work to be extracted from the turbine, and in order to achieve that higher amount of work, you need to add the amount of fuel, and accordingly you will be having your V9 to be lower. Okay. And since I am increasing my fan pressure ratio, so I will be having my V10 to be higher, and that is what is reflecting here. Okay. Since this we are discussing about the turbine entry temperature, that is fixed 1400 Kelvin. Suppose if I will be taking this turbine entry temperature as say 1600 or 2000, accordingly my thrust will be going to increase. Okay. So, we will be discussing this in the next. Okay. Here this is representing my specific thrust. So, my mass flow rate, that is constant, that is the reason why with increase of my thrust the specific thrust is increasing. Now, let us see what is happening with the specific fuel consumption. So, it says when we are increasing our fan pressure ratio, our thrust specific fuel consumption is going to be decreased. Okay. Now, this we need to be very careful when we are discussing. So, in terms of say fuel efficiency. Okay. Let us see what is happening in terms of efficiency. Now, since this is my flying condition, I will be having three efficiencies. So, let us try to look at what all these efficiencies are. So, this is representing my propulsive efficiency. You can see this efficiency is in the range of 70% to 85%. Same way here, this is representing my thermal efficiency. It says by increasing the fan pressure ratio, our thermal efficiency is going to increase. Same way my propulsive efficiency also is increasing, and that is what will be reflecting in terms of increase of overall efficiency. So, this it says like by increasing the fan pressure ratio, we are able to increase the overall efficiency, and that is what is a requirement for our commercial aircraft. Okay. Slowly we will be discussing in terms of requirement also. Now, let us look at the next parameter. It says effect of compressor pressure ratio. Here in this case we are putting fan pressure ratio, turbine entry temperature, bypass ratio and mass flow rate to be constant. So, let us look at what is happening. So, when we are increasing our compressor pressure ratio, it has no impact on my cold thrust. So, that is what will remain nearly constant, but at the same time for the hot thrust we will be having the reduction in the thrust with increase of compressor pressure ratio. Reason, as we have discussed earlier, we need to be careful in terms of what is happening with my exit velocity and what is happening with our fuel air ratio. Okay. Now, this is representing my specific thrust. So, this trend we can say it is in line to what we have in terms of our thrust. Same way here, this is representing my thrust specific fuel consumption. So, you can say by increasing the compressor pressure ratio, we are decreasing, or say with increase of compressor pressure ratio, my specific fuel consumption is going to decrease. Now, this is what is giving indication if we want to make the fuel efficient engine, we can go with increasing the fan pressure ratio, or maybe we need to go with say increase of say compressor ratio. Okay. Now, here this is representing our all three efficiencies. It says again here if we will be increasing our compressor pressure ratio, we will be having say rise of say thermal efficiency, we have rise of propulsive efficiency, and that is how we have increase of overall efficiency. So, in the flying condition, with increase of your pressure ratio, it improves the performance in terms of efficiencies. Okay. Now, let us take the parameter which is of great importance, say bypass ratio, putting all the parameters to be constant, and here interestingly if you observe, it says with increase of bypass ratio my cold thrust is going to increase, but at the same time the hot thrust is decreasing drastically. And if we will be adding this hot thrust and cold thrust, it says by increasing the bypass ratio, basically we are decreasing the thrust capacity even in the flying condition. Okay. So, this will be reflecting in terms of say thrust specific fuel consumption and the specific thrust. So, it says like if you are increasing our bypass ratio, we will be having the decrease of thrust specific fuel consumption. Okay. Now, in terms of efficiency, again we will be putting, it says with increase of our bypass ratio, basically we are increasing our propulsive efficiency. There is a slight increase in thermal efficiency, but in overall sense we will be having the rise of thermopropulsive efficiency or overall efficiency. So, effect of each of these parameter, if you look at carefully, you will realize it has been highlighted with a different color. It has its own meaning. So, when you are doing your calculation, you do your calculation with pen and paper, and maybe later on you can make a code. With using that code you will be able to calculate. See here in this case, this velocity parameter, that is what will be decided whether your nozzle is choke or unchoke. So, that is very important. So, you need to do this calculation, parametric calculation very systematically. Okay. Now, let us look at what is happening with the turbine entry temperature. So, here in this case we can say if we are increasing our turbine entry temperature, my hot thrust that is going to be increased. It is not having much impact on cold thrust. So, overall thrust by increasing the turbine entry temperature, we will be able to achieve higher thrust. And here in this case my specific thrust, it is in relation with the with the thrust, and my mass flow rate it is constant. So, that will be giving with increase of my turbine entry temperature, we will be having the rise of specific thrust. And similar to what we have seen for our ground condition, we have increase of thrust specific fuel consumption with the increase of turbine entry temperature. We must realize here, in order to achieve the higher turbine entry temperature, we need to inject more amount of fuel, and that is what will be lead to increase the thrust specific fuel consumption. So, the thing is, what is our requirement, what we want to achieve, based on that we need to decide with these parameters. So, let us look at what is happening with the efficiency. So, turbine entry temperature, that is what is changing my efficiency trend here. So, it says with increase of turbine entry temperature, we will be having drop of propulsive efficiency, drop of thermal efficiency, and that is how there is a need of reduction in overall efficiency. So, it has adverse effect in terms of efficiency. Same way it has effect on thrust specific fuel consumption. Again, this is what is specific with what temperature we are discussing, what fan pressure ratio, what compressor pressure ratio we are selecting, what bypass ratio. So, we have infinite number of parameters which are present, and that is how, if you recall, in introduction lecture I was talking about application of AIML in order to do the design. So, you can understand we are having lot of data, that is what is available with different combinations. You can use this data in order to calculate the optimum solution. That is what we say in terms of data analytics. Okay. So, this is just for the representation purpose in order to understand how my parameter, cycle parameter, that is what is affecting my performance parameter. Okay. Now, let us look at what is happening with the mass flow rate. With increase of mass flow rate, we can say we have increase of fan mass flow rate, increase of say my core mass flow rate, that is what will be reflecting my area change, and it says both say my hot thrust and cold thrust, they are going to increase, and that is what is giving me rise of total thrust. And here in this case it says my thrust specific fuel consumption, that is what will remains constant. And in terms of my area, you can say with increase of engine total mass flow rate, we will be having increase of area both for say nozzle for fan as well as nozzle for my core engine. Okay. And this is representing our thermal efficiency, overall efficiency, and propulsive efficiency. So, here also let me put the point, we need to be very careful in terms of selection of mass flow rate, because that is what will be lead to increase the size of the engine, and that is what will lead to increase the weight of the engine, that will be increasing the drag. So, that is the reason why this optimization of the inlet mass flow rate also is equally important. Now, let us look at what is happening with the flight Mach number. This is of our interest. So, here in this case, just look at what it says, say we are having this as our mass flow rate condition, okay. And in this case when we are increasing our flight condition, we know our design condition is 0.9. So, let us try to increase the flying Mach number in the range of 1.8. It says the thrust will be increasing because both hot and cold thrust they are increasing. Now, if we look at in terms of say lower flight Mach number, that is what is the case for commercial aircraft, we will be getting our thrust to be lower, and this change it will be reflecting in terms of change of specific thrust. Be careful when we say my flight Mach number is changing, accordingly my density will be changing, accordingly my pressure will be changing, my temperature will be changing, and that is what will be giving you the change in mass flow rate. Okay. So, be careful, it has nothing to do with the constant mass flow rate here. So, here on top also you can understand that part. This is representing the specific fuel consumption, and it says with increase of flight Mach number, the thrust specific fuel consumption that will be going to increase. Okay. And this is representing what we say in terms of all three efficiencies. So, my propulsive efficiency that is going very high if I am flying at very high Mach number. Okay. So, you can understand what is the benefit of flying at high Mach number. Same way my thermal efficiency also shows the increasing trend, but majorly my propulsive efficiency contributes more in terms of overall efficiency. Okay. So, this is very important for us in order to realize what is the effect of flying Mach number. So, till now in last lecture we were discussing about the flight condition, about the ground condition, and in this we are discussing about say flight condition. Let us try to compare these numbers here. So, here in this case it says for the same engine, if I am running that on the ground condition, it says my net thrust is 20 kilonewton, but when we are flying at particular altitude at particular speed, for that my thrust is going to reduce. Okay. So, you can understand what is the effect of my thrust requirement at particular altitude. Same way, if we look at my thrust specific fuel consumption, for the flying condition we have our thrust specific fuel consumption to be higher. Now, propulsive efficiency, that is what will be coming into the picture. If you look at this number is high on site, thermal efficiency is lower compared to what we have in terms of our ground condition, and people they are more interested in overall efficiency or say thermopropulsive efficiency, that is 22.27. So, let us try to compare what all parameters we have discussed. It says like we will check with the variation of fan pressure ratio, putting all other parameters constant, and here in this case we will be discussing about the flight condition and the ground condition. So, just look at carefully. Here in this case, say this full line, that is what is representing the ground condition, and this dotted line which is representing my flight condition. So, we can say in my flight condition my cold thrust has major impact. Similarly, for the hot thrust this variation is not that much with a change of fan pressure ratio. Okay. And this is representing the variation of total thrust. Okay. Now, in terms of say specific thrust, we can say for the flying condition my specific thrust number will be lower compared to ground condition. Same way, if we are comparing the specific fuel consumption, it says for the flying condition we will be having this condition to be higher. So, thrust specific fuel consumption, that is increasing with the fan pressure ratio when we are having flying condition, and that flying condition is 0.9. Maybe if you are flying at 0.8 you will be having different condition. If you are flying at say 0.7, this condition will be different. So, you need to optimize the flight Mach number for that condition. Okay. So, that is the reason why it says like for commercial aircraft you will be having flying condition, maximum flying condition it will be in the range of 0.8, 0.85. For fighter aircraft it will be these days people they are talking about more than 2. It depends what is the kind of aircraft you will be using. Okay. So, all these terms are relative term. We are putting this for the comparison purpose. This is not the generalized chart for single spool turbofan engine, be careful. Okay. This is for our clarity and understanding. So, here in this case we have seen for the ground condition with the increase of fan pressure ratio we have our thermal efficiency that was increasing. And for flying condition we have observed when we are increasing the fan pressure ratio, propulsive efficiency will be increasing, and that is what is reflecting in terms of increase of our overall efficiency. Okay. Now, let us look at what is the effect of compression ratio. So, in line to what all we have discussed for the both the condition, here for the flying condition my Mach number, that is what will be affecting here, and that is the reason why my thrust requirement, that is what will be lower under flight condition. Okay. And here in this case we can say this is the specific thrust. This specific thrust requirement that is higher for my ground condition. Okay. This is representing the thrust specific fuel consumption. It says with the increase of compression ratio we will be having say reduction in thrust specific fuel consumption, but this thrust specific fuel consumption for the flying condition is higher. The reason you must realize here is in terms of what is the amount of fuel, that is what is required. okay, and what is the amount of thrust we have. Okay. Now, here we will be putting this efficiency term. So, we have seen for the ground condition with increase of compression ratio our thermal efficiency is going higher. At the same time, for the flying condition we have observed with increase of the compression ratio or compressor pressure ratio, propulsive efficiency was increasing, and that is how the overall efficiency is coming to be higher. Okay. Now, let us look at what is happening with the bypass ratio. So, the train for both ground condition and flying condition they are nearly same, but we can say the amount of thrust which will be generated under flying condition that is lower compared to our ground condition. Okay. And this is representing the specific thrust for both flying condition as well as for the ground condition. For thrust specific fuel consumption, we can say it has increased by more number when we are having this bypass ratio to be higher. Okay. And this is representing we have in terms of thermal efficiency, propulsive efficiency with increasing the bypass ratio. Basically, we are increasing our thermal efficiency as well as our propulsive efficiency, and that is the reason why under flying condition our overall efficiency will be going to be higher. Okay. Now, this is representing by turbine entry temperature. So, this discussion we have already done with, and it says my thrust specific fuel consumption for flying condition it is coming to be higher. Okay. And here we have discussed, say turbine entry temperature has inverse effect in terms of efficiency with increasing the turbine entry temperature, both thermal efficiency, propulsive efficiency that is going to be reduced, and that is what will be reflecting the overall efficiency to be lower. Okay. Now, in terms of say mass flow rate, we can say this mass flow rate has impact similar to what all we have discussed for both ground as well as flying condition, and my area requirement on the ground condition is lower compared to the area requirement for the flying condition. Okay. And this is representing our all efficiency terms. So, for constant mass flow rate configuration our thermal efficiency and propulsive efficiency that remains constant, and that is the reason my overall efficiency has no effect. So, this all will be giving us idea about the conditions what we say flying condition and ground condition. Let me put the point here. What ground condition we are discussing, you can say it is a sea level, standard sea level condition, but the flying condition that is what we need to decide with at what altitude we are flying with. So, if you recall in week 2 and week 1, say very first week we were discussing about flying at particular altitude in order to take the benefit. So, now just try to correlate what all we have learned in earlier classes. That will give you more joy in terms of understanding. Otherwise, these plots, this discussion, it will not make the sense. Okay. So, which parameter has major influence? That is the reason why thrust we have kept separately in terms of hot thrust and cold thrust. That is what will give you more clarity, more understanding. Okay. Now, with this we say we are discussing about very first we already have discussed about forward fan unmixed single spool configuration. From next week we will start with forward fan unmixed two spool configuration, where we have focused on two kind of engines. First, that is what is fan and low pressure compressor on one shaft. Secondly, fan that will be driven by LPT and compressor that will be driven by HPT. So, now I am sure you are able to understand what we mean by turbofan engine and how this calculation for cycle parameters need to be done, how my energy balance and work balance need to be done, Based on that, how do we calculate the parameters like exit velocity from the nozzles, and from that how to calculate the performance parameters. So, with this we are stopping here. I am sure you enjoyed this first session for the turbofan engine. As we move ahead, we will try to put additional things, and we will discuss say new engines or the engines which are having this kind of configuration that will give you more joyful moment. So, thank you very much. We are stopping here. See you next week. Thank you.